Hello, Algebra 2 students. This is Mr. Wagner. I'm not going to be able to make it in today, but I'm going to give you hopefully the best resources so you can prepare for today's lesson and do the homework. As always, please go to Canvas and you'll see the unit, radicals, and rational exponents. At the very top, before any of the lessons or any of the days, you'll see the examples to know from the Big Ideas text. So if you click on that, it'll take you to a file which shows you, based upon the date, which examples we're covering and which page from it. So we've already done the ones on page, for yesterday we did that. So today these are going to be the ones that you can go over, okay? So let's see, somebody's already on there, cool. But those are going to be the examples that you're going to go over. So what I'm going to do, I guess, over those first, but I'll go over some of those kind of with you in just a moment. But also what I'm going to do is I'm going to show you. Okay, so this is what we're covering today, radical operations with radicals. Like I said, you saw those examples. You may want to go over those. I'm going to talk about them in this video right now. When you're done, there's also a sheet that one of the other teachers made that has some good shortcuts and notes that can help you with this unit as well. You can open that up. It's got helpful properties kind of summarized here. So those might be some notes that can help you to do this assignment for today and get the learning. But what I'm going to do next is I'm going to go into the textbook and look at those examples. Okay, again, the first example for today is example 2 on page 245. Okay, let's see what page I'm on, right? 245, there we go. So example 2, okay. So the important thing about this, a few things about it you may want to also review whenever you see in the textbook. And by the way, if you're wondering where am I going to get the textbook, it should be available online through Clever. Or also, if you're in my classroom, you will see a shelf in front of the big desk. And it's got Algebra 2 text, so you can take those out and look through it, work through the problems. And remember, the answers for the odd questions should be in the back, I believe. But make sure to show your work. Don't just check the answer. Make sure to show your work so that I can give you credit for completing your work and learning, of course. Again, you review this right here real quick. I think a really important thing is this particular principle right there, understanding that these two are the same thing. It gives you an example here that both of those are rooted n, right? And you can break them apart and have an equivalent expression like that. And that's what you're going to be using for this property. Same with division as well. If you've got a fraction that is the whole fraction is taken to the root of something, you can break it apart, the numerator and the denominator, to that same one. Okay, so that's kind of what's going on in A and B. So when it comes to simplifying, we can't break down 12 into a root of 3, right? We can't break it apart into 3 things that are the same and simplify it that way. I mean, we probably could. Well, we could pull out. Now we can't even pull out an 8, right? So we can't pull out anything of the 18 either. But when we combine them, then all of a sudden we get another number that we can then root. Now, here's the key thing that I want to get across with this one. So I'm going to pause it and get another notepad. Okay, so I've got the problem back over here. So how would you know to take it and rearrange it so that you could actually break it down and turn that into 6? Part of it comes from realizing, well, what are the factors that make up the 12? And number one, I think it really starts with, what root am I dealing with? Because remember, on the board in my classroom, we should, at least in the beginning, start looking up at the board or have a list of our own cubes and squares and powers of 4 that helps us to figure out what number we might be able to simplify with, right? So when it comes to cubes, 1 cubed, right, just 1. 2 cubed is 8, 3 cubed, 4 cubed, right? 5 cubed even. So we might say, well, hey, we can't pull out 3 things from the 12. We can't do it with the 18. But what if we combine them, since we know that we can combine them like this? Well, you may want to think about it like this. What is a 12? It's a 2 times 6, which is a 2 times 3. And then it would be multiplied like this, right? And this is 2 times 9, which is 3 times 3, right? Well, let's see. Now that we take these and we combine them all together, we're going to put them into one bracket like this, right? You got, how many 2's do you have? You have 1, 2, 3. So you got 2 to the 3. And then you got 3 3's, 3 to the 3. And now when you pull a cube out, you can do it, right? Because you got 3. So this 2 comes out, becomes a 2. And the 3 also is a cube, which becomes a, my bad, becomes a 3. And then you're left with basically just 1, which is just 1. So 2 times 3 equals 6. So part of it is being strategic and saying, well, hey, I can't simplify this by itself with a cube root or this, but what if I combine them? What are the factors? Can I pull out 3 things combined all together when I have them like that, right? And so it gives you more opportunities to pull stuff out and simplify. All right, so something to look for when you are doing this kind of a problem. Okay, so what next? Here, they're just using this property here to put them together because, again, with a cube 4, I should say, fourth root, you can't really break this one down. Same with this, obviously. But all of a sudden, you put them together as one thing, one term, and you simplify it, and yeah, you can get a 16. And remember, it's the power of 4, so you're going to start thinking, hey, what can I pull out of power of 4? Well, 2 to the 4th is 16. 3 to the 4th is 81. Again, those are on the wall. They better be on my board still. I hope nobody erased them. But yeah, that's what you look for strategically. Okay, so that's what you're going to do when it comes to example number 2. That's the kind of thing you're going to be doing to simplify. Here's another very important concept. And knowing when something is in simplest form, when you're dealing with a radical with an index n. There's 3 conditions, very important to understand because these are going to be on tests and quizzes. It's going to say simplify, and you're going to have to make sure all these 3 are simplified. So I'll let you read these. Okay, you can't have a fraction in the radicand. The radicand is this thing, remember that. It's the square root bracket or whatever, radicand. And you can't have radicals in a denominator of a fraction. Like, for example, if you're looking at b down there, that's a radical in the fraction, in a fraction. You learned about how to rationalize that when you were in geometry. Sometimes you ended up with root 2 or root 3 in a fraction, and we had to rationalize that. Today, that lesson is not about that, so I'm not going to spend time on this today, but you're going to have to know that tomorrow, Friday, or at least the next day, whenever you're watching it. Okay, now I'm going to go to the next example. This is kind of a long video because I'm going to try to shove 3 examples into it. So I apologize, but I'll try to go as quickly as possible. By the way, don't forget, especially since I'm not there today, that there are times when you get tutorials that are videos, okay? So not only that, but you may be in this section right here saying, hey, I need more guidance. Like, for example, previous example, number 1. Whenever you're in the online portion of this textbook and you see these little buttons here, basically it's telling you, it'll show you a video. So if you're like, hey, how do I do that? I'm a visual person. I like to actually see the movement of somebody writing it out and working through it instead of just seeing something like that that seems to be kind of static. And then also if somebody's explaining it, that's nice. So these are good videos. If you're on a particular example, usually you're going to see some videos that have those kind of tutorials that you can, let's see, the next page probably has it, I bet. Let's see where they're, okay, they wait until they get down here, monitoring progress. So all of these right here are going to be little things you can click on to see a video. Okay. All right, so what was the next one that we need to cover? The next one is going to be example 5 on the next page. Okay. All right, so what's going on here? When you're adding and subtracting, you're not simplifying things that are multiplied, but you're adding and subtracting radicals and roots, okay? There's an important thing to remember. Let's see if they've got a little note before that. So let's look at this. Radical expressions with the same index and radicand are like radicals. Okay, I'm going to give you a very simple example of what you know from Algebra 1. So let me go ahead and come up with a new, oops. I guess I need something to write on, one moment. Okay, let's go back to Algebra 1. If we have, oops, where's my pen? There we go. If we have 3x plus 4x, we can simplify that, right? We can combine like terms. Or like terms, why? Because they have the same variable. And what do we do to do it? You can probably just automatically in your head, you're saying 7x, right? We know that, but technically speaking, what is it actually? Well, it's actually the fact that you're factoring out an x, but it's going to be 3 plus 4 times x. So you're literally factoring out x. Now I show it on the right side. A lot of times we show it on the left side when we factor something out, but that's how we end up getting 7x, okay? So that might be obvious. What if we had ax minus bx? What would that be? Well, both of them have an x, so they're like terms. So then what you would do is you'd pull out the a and the b like that. Literally, you're pulling out or factoring by the x. So that's what you would have, right? So again, the important thing is you've got the same variable raised to the same power. I cannot combine 3x squared plus 4x. They sure, they both have an x, but they don't have the same exponent. So I cannot combine those. So keeping that in mind, let's go back and look at example 5. So here you see, okay, so here we see this. They're the same because what do they have? They have the same information, that root 10 to the fourth root, 10 to the fourth root, sorry. In both, those are, in a sense, they're like the x's. You have one of these, there's no number in front, which implies that it's one of these, plus 7 of these, get you 1 plus 7 or 8 of those, okay? Same thing when you've got it rational exponent. You've got 2 of these, 8 1/5, and 10 of those. Together, you add them up, you get 12 of those. Where'd that go? There it is. Okay. Same thing over here. Now, what's this though? This is a little bit weird. What is C? They don't look like they're exactly the same, do they? But what have they done on C? They converted C into, they broke it down because they were simplifying is what they were doing basically. Because remember, a cube root, you could simplify out. So they basically rearranged 54 as 27 times 2 because, again, strategically, they're thinking, what is a perfect cube root? 27. Is 54 divisible by 27? Yes, it is, right? So that's the benefit you get. So they re-expressed just this one as these two together as the product. And then these two are the same right now. And then they took the 3 out, and they are left with yeah, the 3 out from this one becomes 3 times, yeah, 3 times that. Sorry, because remember, this is still a product. Sorry, they took the 3 out. This whole thing became 3 times that. So I had to look at that for just a second. So that's why this piece right here, this whole thing comes into that, because it's this thing whole right here becomes the 3, but it's still, that 3 is still multiplied by that. And then all of a sudden now you have the same 2 root 3, and then they factor out to 3 and 1. That's kind of a complicated one, but it's a great one. So, okay, let's see, what next? Again, there's more down here. Again, sorry for such a long video. I usually try to keep them under 5 minutes, but I'm trying to get the whole lesson in one video, so you don't have to keep clicking different videos. All right, so now I'm going to look at the last example, which is example 7 on page 247. We actually did this yesterday, so we're going to just come back and look at it again. Yeah, it's one of these where you basically have, you know, writing variables in simplest form. So remember how this goes, right? So the goal is to take that A, or to see if you can pull out 5 of something. 4, there's no way you can break that down. So that ends up getting stuck in there to the very end, right? But A is to the power of 8. So they said, hey, there's literally 8 A's. I could list a product of 8 A's together multiplied, and I would be able to pull out 5 of them because we have 8 of them. And so what they did is they show the A down here being re-expressed instead of A to the power of 8, A to the power of 5, A to the power of 3. Why? Because they knew when they broke it down to the power of 5, they could pull that A out, which they did, and that ended up coming up over here. And what did I do there? I do not like that. Hold on. Okay, so for some weird reason, when I click on it, it expands the screen radically. Speaking of radicals, that's a free joke. Feel free to tip the waiters on the wait staff on the way out. Anyway, let's see. So that's why we got A3, but A3 is left over after we take out the A5 B10, right, etc. So we did this problem yesterday.